Oh, the screen is really getting bad. I've got to see another semester.
It's that they need to fix
It's
the
like
lens.
creeping. The darkness
Is it like
is creeping.
It's a lens.
It's a lens thing? Yeah, I probably just need to get up there and fix it. All right, so we've got 4 pairs of structures, and we have to decide if they are isomers, if they're the same, or if they're unrelated, just different molecules completely. This is a common way to ask about, or to ask about structures like this in something like a multiple choice exam when you wouldn't be able to draw them. Because really, to do these effectively, you have to be able to draw them. You have to be able to manipulate them so that you can compare them. And that means either, so the technique to this, there's really 2 ways that people usually do it that's successful. One is to be good enough and confident enough at naming these structures that you can come up with a name for each one. If the names are the same, you know they're the same. If the names are different, but the formulas are the same, you know they're isomers. And if the names are different, formulas are different, then they're unrelated. So that's one way to do it.
Oh, that was a question. Oh, I get it now.
The other way to do it is to, the other way to do it is to take one of the structures and put it in the form of the other one. So if you've got a line structure and a condensed structure, maybe you make a line structure out of this so that you can more easily compare them. Or maybe you make a condensed structure out of this so you can more easily compare them, whatever. So that's kind of the way to do that, one or the other. Either use the names or put them in a comparable form. And we'll look at both. Yeah, so you'll see something like this on the final. Similar. And I think if you look at the like exam 3 or the other stuff that's posted from last year, you'll see some questions like this. Okay, so in this first one, let's do the name idea. How do you name this structure on the left? How would you name it? Yeah, you find the longest chain, which is the whole thing in this case. Count the carbons. 5. So what's that name? There's no substituents. So it's just pentane. What about this one? Same thing. Count the carbons. No substituents. Pentane. So what does that make those two? Same.
Yeah, me too. Yeah, I was doing it around too. I get it.
I thought those were the same thing.
No, I was like, what are you asking? But that makes sense.
Yeah, classify as one of these 3. Okay, so this one we could do the same thing. So we already have a name on the right. We could get the name for the left and see if they're the same or not. Or we could try to draw this structure from this name and see if they're the same. Which one do you want to do? Should we draw it? Okay. So when we draw, we start from the main part, whether it's a chain or whatever. In this case, it's cyclopentene. So we're going to draw a cyclopentene. Okay, doesn't matter where you put the double bond, somewhere in there. And then we're going to number it. So it's 1 cyclopentene, which means that the double bond is between 1 and 2. So that means we have to number around this way, or the other way. But anyway, start at the double bond somehow. And then we add our substituents. So we've got 1,2-dimethyl. So that's 1,2-dimethyl. So is that the same as that? It's not the same. Is it unrelated or are they isomers? How can you tell?
It's unrelated.
Why?
Because the carbon bond and the other one doesn't have. Wait.
What's the difference between isomers and unrelated structures? What do isomers have that unrelated structures don't?
Isomers have the same formula.
Yeah, isomers have the same formula. So if you're not sure, you should get the formula and compare. So let's do that. We count up the carbons. So 1, 2, 3, 4, 5, 6, 7 carbons here. 1, 2, 3, 4, 5, 6, 7 carbons here. Okay. Then we count up our hydrogens by looking at how many we need at each spot to get to 4 bonds for each carbon. So this carbon has 1 bond. We need 3 hydrogens. 2 here, 2 here, 1 there, 3 there, 1 there. I get them all? Maybe? Okay, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's C7H12. I'll do the same thing over here. 1, 2, 3, 4, 5, 6. Those don't need any. 7, 8, 9, 10, 11, 12, and nothing there. So this is also C7H12, and that makes these two isomers. Same formula. The other way you can identify these as isomers is you can think about how to make one into the other. If you take off this CH3 and move it over to here, you have the same thing. So if you can like build the other one with the same parts, that's another way of saying that they're isomers without losing any parts.
I thought you were just displaying the structure and the name, and they were both the same. I didn't, think to actually.
Yeah, these are different then. So you have to decide whether these. So if you're not clear about that, ask, and I can clarify that for you. Yeah, I could totally clarify that for you. All right, so same question. How do you want to do this one?
We'll count the lines. So it's
Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, and no substituents. So this one is octane. What about here? 1, 2, 3, 4, 5, 6, 7, 8. So that's also octane with no substituents. So those are also the same. Okay. And what do you think about D?
I think they're different.
Okay, let's look at it. So since we have a name here, let's try to name this one. Let's do it that way this time. So we have to count our chain, our longest chain, and this one has a double bond, so we want the double bond closest to 1 as possible. So that means we're going to start over here and go 1, 2, 3, 4, 5. So that makes this a 2-pentene because it's pentene and the double bond starts at 2. All right. So now is it cis or trans? It is cis because if we imagine a line through here, kind of it's lopsided off to one side. It's not even on both sides there. So like the two hydrogens here are on the same side. So this is cis 2-pentene. That's cis 2-pentene. So these are also the same. All right. Okay, some names or some structures. What did you get for the first one? Anybody confident about that one?
I forgot what I wrote down, but I think it was
Methylbenzene.
Close.
Oh, ethylbenzene.
Ethylbenzene. Yeah, you've got a 2-carbon substituent coming off of a benzene ring. So this is.
So that line coming off on the side, it counts. You count it as 1?
Yes, remember there in a line structure, there's a carbon at every bend and every end. So everywhere that the lines come together and then also at the end. So that's 1, 2 carbons. So that's going to be a CH2, CH3. There is a Y.
No, it's about benzene.
Oh, okay. I'll give you credit for that. There actually is a separate structure called benzyne, but that's okay.
3, right? If it is a Y, it's 3.
It's a triple bond, yeah.
But that's not a triple.
No, it's just benzene.
3 double bonds.
Right. It's just called benzene. Okay, what about 1122 tetrachloroethane? And I wasn't specific about whether I wanted a line structure or just with all the carbons drawn out. So you can do it either way
I
here.
put a C-C and then on each C, chloro on each, yeah. One on top, one on the bottom, and the same thing on the other one.
Like that?
Yeah.
Okay, is that right?
Because tetra means 4 chloro.
Right. So we've got 2 carbons for ethane. 1, 2. 2 chloros on 1 and 2 chloros on 2. So is that it? Missing one part. It's got to have a single bond because it's ethane. So what isn't shown here? Hydrogen. These carbons need to have 4 bonds. So we got to make sure to have hydrogen on those carbons as well. If we draw it in the line structure form, we don't show the hydrogen. But if we're going to draw it with letters, we have to show the hydrogens.
Oh, I should have done it that way.
Right. So that would also be a correct way to express the structure.
And so that would be the same.
Yep.
Okay.
So here we have carbon 1 and 2, and here we have carbon 1 and 2, each with 2 chlorines. Okay, and then this one, we find the longest chain. And that's going to be just straight across the middle here. Do we want to start numbering from the left or from the right?
I mean, like,
Why?
Right. This is closest to.
Yeah, closest to the substituent. So we go 1, 2, 3, 4, 5, 6, 7, 8. And then that's going to be what, octane? And then we have a 2-carbon substituent on 3 and a 1-carbon substituent on 4. So that gives us 3-ethyl 4-methyl octane. Okay, and then the last one, cyclopentene. Just like we did up there, that's going to be a 5 carbons with a double bond, and it's 1 cyclopentene, so we can start numbering like we did before. So then our substituents are 3,4-dichloro, which means we're going to have 3 and 4 and a chlorine at each one. So there's the structure. All right, and then completing some reactions. We have hydrogenation first and then hydration second. So the hydrogenation will add hydrogen across this double bond, so here and here, which makes for that structure. No? You weren't here on Monday.
no, I didn't get the.
Yeah.
Right, but I knew you had to draw it at least.
Okay.
Actually, I think I might have run maybe off by a little. I think I put an extra 1 branching off that was that high.
All right.
That's what I did. That's what I did. I don't know why. See, we all did that. And I wasn't here, they were.
So another way you could draw this is by actually drawing out those hydrogens. All right, so we can say that we can make explicit that we put those hydrogens there, but we don't need them because in the line structure, you don't need to draw the
But it's
hydrogens.
not wrong.
It's not wrong, no. You can always add more to a line structure. You can add the hydrogens to it if you want to show them for some reason, but you don't need to. It's not necessary in that structure. All right, and then here we see the product of a hydration. Remember, hydration adds OH to 1 carbon of a double bond and H to the other carbon. So there's actually 3 right answers here because this could come from a double bond at any of the positions around there. So that means the possible answers would be this one. Oops. Uh-oh. What's going on here? Just not going to draw anymore? Just going to freeze everything?
It's time to redraw it.
It's tired. It says quit already. Are we out of a memory or something? Well, that's working. Okay. Let's try it again. So that's one possibility. That's another one. And you can have a double bond down there too. Those
But
will all
it
be
has to
correct.
be on the bottom.
No,
The line could have been on the top.
line could be on the top. Yeah. Doesn't matter how you draw that. You mean like that?
Yeah.
Yeah, that's fine. As long as you show a double bond at that spot between those 2 carbons. Yeah. So that's a quiz. Any questions?
You tricked us with that isomer one again.
I tricked you.
Yeah.
How's that tricky?
I don't know, I think I just
Okay.
put same. I didn't really register either, but no, okay.
Well, they were mostly the same, so you got probably most of them right if you did it that way.
That would be a perfect quiz if not.
I thought that was.
All right. Well, so we got a half an hour. What do you want to talk about? How's studying going? Going back through some of that old stuff? This is a good time to, no, I'm not right now. When you're studying for final now, pull up some of those old exams, the ones we did in this class and the ones from last year, and the other stuff that's up there, and just open them to random places and see if you can do it. You know, pull up question number 14 from the first exam and see if you can do it. And because chances are a lot of that stuff you can, because we've been building on it, we've been using it, and so it's been reinforced throughout the whole semester. But then there's probably a few subjects that you're a little rusty on, and that's where you're going to want to focus your studying for the final.
Do we have, are there the answers for our exams out there? No, not the corrected ones. Or we went through them in class?
No, we went through them in class, so you may have them, and you can
Oh, we would
always
have to have it on.
ask me.
Is there a, yeah, okay. can
There's
you
no
just-
posted answer keys.
Not from the old ones either.
Right.
But are there blank copies of all of the exams that we took in there?
I don't think they're posted on Blackboard. The last year's exams are up there, and your exams you should have,
just
right?
a copy of them, right?
If you want a digital copy, I can send you one. You know. Whatever. So. Practice some of the moles. Anything in particular? Just in, like equations or like
Yeah,
converting
like
from grams to
problems, like
moles?
word problems.
Okay. Anybody have one offhand that we could pull up here that you've been working on? Yeah. Okay.
Do you put the role concentration and third chart on the back?
Okay.
You still with that chart?
I know, I get stuck on these things.
All right, let's look at this one. What is the molar concentration of a 500 milliliter solution containing 2.5 grams of calcium chloride? Oh, can't really see that. So first key here, molar concentration. What does that mean? What kind of a quantity are we going to need to get? Moles, right? Molar concentration is molarity, which is moles per liter of solution. Moles of solute per liter of solution. So what do we have? We have our volume of solution, and we have grams of solute. So we need to convert grams of solute to mole of solute and then divide by the volume of the solution. So let's do that. We also need the formula of calcium chloride. What's that? Right, CaCl2. Right, calcium is a 2+ ion, chloride is a 1- ion. So we need 2 of the chlorides to balance out the 2+ and the calcium. Definitely review your naming stuff if you're still a little rusty with that, because that will be important. All right, so we can come up with a molar mass of this. That's going to be 40 plus calcium plus 35.5 for chlorine plus another 35.5 for another chlorine. That's 111. Right? You think? Yeah. So that's 111 grams per each mole, each one. And we have 2.5 grams, so we have to do a conversion there. 2.5 grams calcium chloride. And then we want to convert grams of calcium chloride to moles of calcium chloride. So that's going to be 111 grams per mole. We just calculated that. So then we divide 2.5 by 111. Don't forget your calculators for the exam, by the way. It's going to be 0.0225 moles. So that's how many moles of calcium chloride we have in 2.5 grams. So if we have that many moles in 500 milliliters of solution, so moles of solute divided by the volume of solution, which is 0.5 liters. 500 milliliters is 0.5 liters. That's going to be 0.045. And that's moles per liter, which is molar. So that's the molar concentration. All right. What else?
I mean, I just calculated my own, but I still want to be able to determine just by looking at it, but like this question right here, I don't know if I'm right or wrong, but I just looked up like the density of water before.
Okay.
And that's how I think it was sinking water, but.
Let's look at that. All right, so this one won't come up on the video, but. So the question is, an object has a mass of 10 grams and a volume of 8 milliliters. Which of the statements about the object is true? It's a solid, it's a liquid, it will float in water, or it will sink in water. So can we say that it's solid or liquid?
No, that's not enough information.
No, it's not enough information. Liquids and solids can have any range of densities. So just because something is a particular density or a particular weight or whatever has nothing to do with whether it's solid, liquid, or gas. So A and B don't really make sense here. But we could tell if it will float or sink in water because we know the density of water. And something that is more dense than, well, I know the density of water. Do you know the density of water? One what?
I forgot.
I don't know.
One something. Well, you're right that
No,
it's
it's
one.
actually 0.998, whatever you round it
It
off.
depends on temperature, yeah. So it varies a little bit, but it's basically 1 gram per milliliter, which means 1 milliliter of water weighs 1 gram. Okay. So that means anything that is more dense than water will sink in water, and anything that is less dense than water will float. So we have to find the density of this. Now it looks like you've done this calculation out here. Find the density, we divide the mass by the volume, so 10 grams divided by 8 milliliters comes out to 1.25 grams per milliliter. That's the density. So is that density greater than water?
Yep.
Yeah, so then that object will sink. Right. The thing that makes this question, or could make this question difficult, is it doesn't say density in that question anywhere. It doesn't say calculate the density of this object and then determine if it will float in water or not. Which actually is also what makes it a good question, because you have to understand what density means and what it's for and the concept of it to figure out the answer there. Circle one?
You wanna?
Okay. Okay, number 4. Consider the following unbalanced equation. C18H32O2 plus H2, a hydrogenation. Balance the equation, and then answer the following question. How many moles of that carbon hydrogen oxygen thing are needed to react with 5 moles of hydrogen? Okay, we'll leave it out there. I'll write it over here.
You get like the ratio?
Yeah, so we need to balance the equation and then use the molar ratio to figure out the question that's asked. So here's our equation. 36. So does anybody see how to balance this?
Yeah, because there's 32 hydrogens is 36, everything else is balanced.
Yeah, the carbons are balanced, the oxygens are balanced. So the only thing is we have 32 and 2 is 4 hydrogens on this side, and 34 on this side and 36 on that side. So to balance that, we've got to put a 2 there. And that brings us up to 36 and 36. Okay. So then, how many moles of this are needed to react with 5 moles of hydrogen? So to get that, we'll take 5 moles of hydrogen and multiply it by the molar ratio, where we cancel moles of hydrogen and get moles of that. And we get that from the equation. What does the equation tell us? Those numbers should go there? 1 and 2. So one of these reacts with 2 of these, so therefore the ratio here is 1 to 2. Okay, so that means that 5 moles of hydrogen react with 2.5 moles of this. Because 5 divided by 2 is 2.5. So D is the correct answer here. So the other question, this was from last year's exam. What is the molecular formula of the following structure? Okay. I'm going to draw this structure back on the screen here so I can play with it a little bit. So there's the structure, and it's asking what is the formula of that structure. The thing that you may not be as familiar with are this wedge and dash notation. Yeah, so all this is, those things just mean bonds. The reason that they're there is they tell us something about the 3-dimensional arrangement of the bonds on that carbon. Remember, carbon has that tetrahedral shape. It's not just squared. So what that means is the wedge is coming out at you, and the dash is going back. Right, so it's kind of like a way of expressing that perspective in flat paper. But all it means is a bond. So we can treat that just like a line, a regular old bond. So let's look at the formula. This has got 6 carbons. We don't know how many hydrogens yet. We'll figure that out. That's the tricky part. And then 1 bromine and 1 oxygen. Got with me so far on that? All right, let's count up the hydrogens and see what we get. So first, we'll count the ones that are shown explicitly. So there's 1. There's another one. Just put a little dot there to mark them. Now let's go around to all the carbons and mark the hydrogens that aren't shown. So this one needs how many? Or has how many? 2. This one? 1. And then we get 2, 2, 2. What about this one? No extras, right? It's got this hydrogen on it, which is shown, but it can't have any more because that's 1, 2, 3, 4 things connected. So that's all our hydrogens. So we count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's going to be C6H11 BRO, which in this case is answer B.
Why does hydrogen have 1?
He's marking the hydrogen.
I'm just marking it
Oh,
with a little dot.
That's not like an.
I'm not saying there's an extra one. I'm just saying there is one to count there. Same with over here. So we don't forget it. A common mistake in these types of problems is actually most people will get it right that count these hydrogens outright and then forget the ones that are actually shown. So we need to make sure to mark those also. You can circle them if you like. I like that better.
so always when you're adding stuff like this up, you split up the O and the H. If you're writing it out, you would break them up. You wouldn't leave it.
You don't need to. It doesn't matter what order you put them in.
So
Now, in a molecular formula is different from a structural formula. A structural formula tells you how things are connected, like CH3, CH2, CH2, CH3, or CHOH, or something like that. That you're right. You'd leave everything together because you want it to show the structure, to show how it's connected. But a molecular formula is just an atom inventory. It just tells you how many of each atom you have. So you split all the atoms up and just put the number for each one. But that's why molecular formulas are often not as useful with organic compounds, because the same formula might have many different isomers associated with it. So structural formulas can be more useful that way.
Can you just do a couple more random mole things?
A couple more random mole things, sure.
Like mole concentration.
There's a question right here.
Okay. Yeah, okay. So this is similar to the one we just did.
There's some there.
Let's reword it a little bit so it's slightly different from the one that we just did. So this one says, calculate the molarity of a solution that contains 200 grams of sodium hydroxide dissolved in 400 milliliters of solution. Let's turn that around and say, how many grams of sodium hydroxide are in 400 milliliters of a 2.0 molar solution. So a different problem. Right. So a 2 molar solution tells us that we have 2 moles in every 1 liter of solution. But we don't have 1 liter of solution, we have 400 milliliters. So should we get more or less than 2 moles in our 400 milliliters of solution? Less, right? These are important things to think about, because if you just happen to flip the thing accidentally, or say here's a common mistake. we're going to forget to convert milliliters to liters. So we say, okay, it's 2 moles per liter. We've got 400 milliliters, so we multiply 400 by 2 and we get 800 moles. So that should, if you're thinking first, okay, should my answer be less or more than what I start with? If you get 800, you know you did something wrong because you know this answer can't be 800. And that tells you, okay, well, what did I do wrong? Then you can go back and look at it. Well, we've gone through some of those before, but it's a common thing on exams for people to just say, okay, I plug this into this way, I do this problem, and not really think about whether or not this really makes any sense. All right, so anyway, so that means we're going to have 0.4 liters times 2 moles per 1 liter means that we're going to have 0.800 moles. Now what's the formula for sodium hydroxide? OH, right? Hydroxide is one of those polyatomic ions, 1 minus polyatomic ion. Make sure you review those. Okay, so 0.8 moles NaOH, and now we need grams per mole. So we're going to take our 0.8 moles and we want to figure out grams per mole. So we're going to add that up. Sodium is 23, oxygen is 16, and hydrogen is 1. So I think that's 40. We add those all together. All right, so 0.8 times 40 is going to be 32. So that means that in this solution, this 2 molar solution, in 400 milliliters of it, we have 32 grams of sodium hydroxide. All right, let's get. We go back and do some really old stuff. Who can give me an example of a pure substance that is a compound?
Isn't sodium? I mean, sodium chloride.
Sodium chloride. Yep. What is a pure substance that is not a compound?
Sodium.
Yeah, exactly.
Yeah.
Something that's an element that only has one type of atom. What's another type of matter besides elements and compounds? There's one other class. You can either have a pure substance or you can have a mixture.
Just blank faces.
Go away there. That's good.
Wait, is water a pure substance?
Yes, it's a compound.
And what would, how can you know? Because some of these, they look like they're balanced out, like the sodium hydroxide, what would be considered like a neutral compound amongst like hydrochloride or sodium hydroxide or?
So that question is asking in the context of acids and bases, not neutral charge, but neutral
okay.
pH.
Okay, just making sure.
So if that question only says neutral, that's really not a good question.
Yeah, that's why I'm.
Because it says-
As to what it asks.
Yeah, because neutral could mean neutral, like the charges balance out, like not an ion. Neutral can also mean neutral pH. So that question should really say which is neither an acid nor a base, or which would be a neutral pH.
I guess you can just always tell you, I mean, even though the question sucks, I mean, if you look at the
That's true.
options.
If every possible option is neutral by charge, then they must be talking about the acid base effect.
You give us one.
I give you one?
Yeah, you give us one
All right.
that we're bound to see.
something you're bound to see.
After you're done, I have one.
Let's see. What are we bound to see?
Can you show me on the electron configuration?
Yeah, you might see something like that.
Oh, yeah, good. No,
I mean, this will certainly be important, but something like this will show up. Which atom does not have a full octet in its valence shell? I'll give you some choices here. Okay, there's 5 choices. Which atom or ion does not have a full octet in its valence shell?
Wait, like for lead?
Yeah.
It says on top it has like 4 bands.
Right. So what does it mean if it's lead 2 plus?
No, it's missing 2.
Right. So then that's your answer, right?
Yeah.
So let's look at each of these. How many valence electrons does aluminum have in its neutral state? 3. Valence 3, right? So if it loses those 3, it's got a full octet because it's lost everything on one shell, so the next shell down must be full. What's next? Neon, noble gas, got 8 electrons, full shell, done. Okay. Fluorine -1, so fluorine's got 7, but it's a -1, which means it's got 1 extra, so that gives it 8. That's a full octet. Lead is the answer, so we'll get to that in a second. Phosphorus 3-, phosphorus has 5, but if it's 3-, that means it has 3 extra, so that's 8. So that has a full octet. Right, 5 plus 3 is 8. So then we look at lead. How many valence electrons does lead have? 4. If it's 2 plus, that means it's missing 2, but that means it still has 2 in its valence shell. So that's not a full octet because it only has 2 in the valence shell.
I would say it backwards, so like if it's like aluminum 2 plus, it means that it doesn't need 3?
No, that means that it is missing 3.
Well,
3 plus means it has 3 more
right,
protons.
that's your figure, well then if it's missing 3, then wouldn't that not be an octet and wouldn't that?
Well,
That's like,
it's so technically, I guess you could say it has 0 electrons in its valence shell, but that doesn't make sense because then it wouldn't. If the valence shell is always the outermost shell, then you can't have one with 0. It's the outermost one that has electrons in it. So if aluminum's valence shell is the 3rd bucket, 3rd shell. So if it loses all 3 electrons out of that 3rd shell, Now the second shell becomes its valence shell, and that
So
one's
you're
full.
saying like in that very last shell, it only has 3,
Right.
and once you get rid of it, and the same thing with, phosphorus and lead.
So let's look at that configuration. Remember we had these kind of 3 buckets,
Yeah, remember, and I would do it.
2, 8, and 8. And so for aluminum, not aluminum 3+, but just aluminum, we've got 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 3 electrons in its valence shell. Okay. So if we now have aluminum 3+, that means we're going to lose those 3. So now this is its valence shell, and it's full. It's got an octet. Let's look at how that works with.
Because you got those from where? Or it's not saying where it got the 3+, it's just saying.
It, 3+ means it lost 3 electrons. Yep. So then phosphorus has 15. So that's 10, 11, 12, 13, 14, 15. 5 electrons in its valence shell. If it's phosphorus 3-, that means we have to add 3 more electrons in. 1, 2, 3. So now that's full. That's got a full octet valence shell.
How about this then, because I don't know how they wrote, I guess, sodium, but it has all these. what is
Yeah,
it?
we didn't do configurations like that, so don't worry about that. All right, that's all the time we've got. Another class coming in. So if you need me, I'll be upstairs until about 3:30 today. Then tomorrow, pretty much all day, except for an hour in the morning. I got to go talk to some 3rd graders.
You guys have a-
And then again, Monday, I'll be here pretty much all day. If you want to be sure to talk to me, you know you're coming in at a certain time, just send me an email, and I'll make sure to be there.
Monday. You could bring your dad to school. And you guys are performing.
No, they're
You're at
bringing a
school,
bunch of
you guys wanna go and
3rd through
report
5th
just for an hour and a
graders
half?
from District 14
Oh.
to talking about stuff.
Oh.
We did it last week too. It was fun.
Yeah,